We are diving into a realm that, well, most people think is pretty much impossible.
Yeah.
Truly scalable blockchain infrastructure.
Right.
For years, the whole conversation has been, bogged down by transaction limits, high fees, all that.
And slow confirmation times.
Exactly. But today, we're not just talking about digital money. We're going to deep dive into an architecture called Terranode.
And this is the system that delivers what they call unbounded scaling for the Bitcoin SV blockchain. It's about fundamentally transforming how large-scale enterprise data moves.
That's the key, isn't it? The data.
That's exactly right.
Yeah.
Our sources confirm this is about building a secure, high-speed foundational layer for the next generation of the internet.
I think Kurt Walker Jr. put it best. He said Bitcoin is often thought of as a currency, but it's actually
The most misunderstood communication technology in a generation.
Yeah.
We're really looking at the shift from just a digital cash ledger to a global data processing infrastructure.
So our mission today is pretty straightforward. We need to get into the mechanics. How does this system even handle over 1 million transactions per second? 1 million TPS.
Without compromising security, which is the crucial part.
And most importantly for you, the informed listener, what are these overlay networks? Why are they described as like a hidden internet being built on top of this secure base?
We're looking for those aha moments, the structural insights that make this whole paradigm shift possible.
Okay, let's start with the foundation itself. We have to set the context for why BSV is the platform for this.
Good point. It's really defined by its commitment to huge block sizes and high throughput.
So its economic model, its consensus rules, they're all just built differently from other chains that focus on small data volumes.
Precisely. If you think about the internet, it's not one single technology, right? It's a stack of protocols, layers. The foundation here, the BSV blockchain, it acts as that secure, immutable base layer. It's the ultimate source of truth, ensuring perfect data integrity through cryptography. The whole platform is just designed for immense capacity.
Okay, so if that's the base, then the overlay layer sits on top. How do we explain this specialized highway, this hidden internet, to someone who gets general web infrastructure?
So think of it this way. The base layer records all the transactions, makes sure they're permanent and secure.
Heavy lifting.
The heavy lifting, exactly. The overlay layer is a set of specialized protocols that interpret that base transaction data in unique ways.
So they give it meaning.
They give it meaning. They transform raw on-chain data into specific applications, whether that's supply chain logs, immutable climate data, or even private communication services.
I see. So you get the security of the blockchain, but with the speed and flexibility of modern web services.
Oh, I got it. It separates the security from the application agility.
And the engine making this all possible, making the base layer fast enough to support these overlays, is Terranode.
Publicly released in late 2024 after, 3 years of intense engineering.
And the sources, specifically Siggy Oskarsson, highlighted the choice of the Go programming language.
Which was crucial for its efficiency in building distributed systems. I mean, this wasn't just another software project. This was serious infrastructure engineering.
It had to be. Terranode needed to break those physical bottlenecks that plague, well, pretty much all traditional blockchain architectures.
Right. Most systems use vertical scaling.
Which is just throwing more power and memory at a single machine.
You just keep making one machine bigger and bigger until you hit a physical limit. You can't make it any faster. Terranode flips that entirely. It uses horizontal scaling.
Meaning you distribute the work across many machines.
Exactly. Instead of one huge server, you have a cluster of smaller coordinated servers working in concert.
Which means the capacity is, in theory, elastic.
It's virtually elastic. As demand grows, you just add more clusters.
Yeah.
And the system actually gets more efficient and its throughput increases rather than degrading. That's the definition of unbounded growth.
Okay, but that immediately raises a red flag for any systems engineer. If you're splitting a massive workload across multiple machines, doesn't synchronization and timing become an absolute nightmare?
It does.
How do you conduct that orchestra of independent processes without it all just falling into chaos?
And that is the core engineering feat here. The sources describe Terranode not as one big piece of software, but as a suite of at least 14 independent microservices.
Ah, microservices.
Okay, they're highly specialized, and they talk to each other intelligently. For example, you have a validator service designed to process transactions through parallel pipelines.
So they're running at the same time.
Simultaneously. This completely eliminates the sequential logjam you find in older architectures. Validation isn't waiting for the previous batch to finish. It's running hundreds of batches at the same time.
Okay, so once those are validated, what happens next?
Another microservice, the one handling block assembly, doesn't have to re-verify everything. It just compiles these already validated subtrees into the final block, and it does it extremely quickly.
So the hardest, most time-consuming work is already pre-approved.
It's done. This shift from a sequential bottleneck to a rapid assembly line is absolutely fundamental to hitting those high TPS numbers.
Let's focus on that speed now, because this is where the subtree breakthrough really changes the user experience. Historically, that waiting period,
The agonizing 10-minute wait.
it's made blockchain unusable for retail, for high-speed data.
Yeah.
How does Terranode get rid of that confirmation wait?
It solves the problem by replacing that sequential confirmation with continuous confidence building. That's the subtree concept.
Okay, break that down.
Instead of waiting for a miner to find the entire block before anyone starts validating, Terranode organizes transactions into these things called subtrees.
Small, verifiable subsets.
Exactly. Small, cryptographically verifiable subsets. And these are broadcast and continuously validated every single second during the mining process itself.
So if I send a transaction, it's not just sitting in a mempool hoping to get picked.
No, it's immediately pre-validated within a subtree. You get real-time confidence.
I see.
The moment your transaction is included, the network starts confirming its validity. So when the final block is solved 10 minutes later, that final assembly is super fast because the validation is already, for the most part, complete.
It's like having every chapter of a book peer-reviewed as the author writes it.
That's a great analogy. So there's no massive delay at the end when you submit the final manuscript.
Which means transactions are functionally confirmed within seconds. That makes it viable for point of sale, for rivaling major payment processors.
And the numbers back this up. The Sustained Global Test Network trials, they've demonstrated performance exceeding 1 million transactions per second.
1 million TPS.
And just for context, Visa typically peaks around 65,000 TPS.
And networks like BTC are what, 3 to 7?
3 to 7 TPS. It's a different world.
And that million TPS figure, that's just the starting point, not the limit.
Not the theoretical limit of the architecture, no.
Yeah.
And when you look at daily capacity, a single terabyte block can hold up to 4 billion transactions.
Which gives you a theoretical daily ceiling of over
500 billion transactions. The infrastructure can handle the volume of global commerce and data processing, period.
Okay, which brings us to the critical security model. How do you maintain integrity in a system processing that much data without forcing every user to run a supercomputer?
And that's where Simplified Payment Verification, or SPV, comes in.
We hear SPV dismissed a lot, as just a lightweight client.
It gets a bad rap. But the sources are clear that Dr. Craig Wright provided a formal mathematical specification for it. He elevated it to a provably secure protocol.
And what does that formal security model guarantee?
It guarantees that an SPV client, even one on a smartphone or an IoT sensor, can confirm its transactions are included in the longest, most valid chain without processing the entire block history.
So it gets the same security guarantees as a full node?
The exact same level of security.
But how? I mean, if I'm not downloading the whole history, how can I possibly trust the validation?
It's the elegance of Merkle trees. An SPV client only needs to maintain the block headers.
Which are tiny.
Tiny. 80-byte summaries. When the client needs to verify a transaction, it just requests a Merkle proof from a node.
And that proof is what? A cryptographic pathway?
It's a short mathematical connection that proves the transaction's inclusion in the block, confirmed by the Merkle root that's already in that little 80-byte header.
So I don't need the whole phone book. I just need the page number and the line that my name is on.
A perfect way to put it. You just need the receipt. This is what enables true lightweight participation, which is essential for what the sources call the blockchain mandala.
The mandala, this is the organizational hierarchy.
Right. At the base, you have the core layer, the Terranode nodes handling global consensus.
Then above that?
The overlay layer, which hosts sophisticated services and enterprise infrastructure providers. And then you have the vast edge layer.
And that's where all the users are, the mobile apps, the sensors, all using SPV.
Exactly. It makes the system both scalable and universally accessible.
Okay, let's shift to implementation. If I'm an enterprise executive, a developer, I don't want to deal with Merkle proofs and block assembly. I just want reliable APIs.
Of course. You want to track your supply chain, have immutable audit trails, or micro-monetization.
And that's where ARC, the Advanced Resource Coordination Service, comes in. It's the bridge, right?
ARC is the abstraction layer. It provides clean enterprise-grade APIs and service-level agreements, SLAs, for businesses.
So it takes all that complexity.
And it presents it through familiar web service tools. It lets companies integrate things like regulatory compliance and global micropayments without ever having to touch the low-level blockchain protocol.
The technical foundation is obviously impressive, but the real test is what people are actually building on this hidden internet. Can you give us some rich examples of these overlay networks in action?
A fantastic one is WeatherSV.
For climate data.
Right. It's building a global climate data infrastructure. They use the overlay layer to create cryptographic proofs of authenticity and to timestamp every piece of global climate data they record.
So it's an immutable climate record?
A provably true foundation,
Yeah.
which is absolutely vital for things like training reliable AI models or for global regulatory auditing. It's not just a database, it's a verified, tamper-proof system of record.
That's a powerful use case. What else?
Another great one is first-set ordinals.
Digital assets.
Exactly. By leveraging BSV's capacity for near-zero fees, we're talking fees measured in single satoshis, they are completely redefining digital asset creation and ownership. They use the overlay network to manage metadata and facilitate asset trading with such low friction that high-volume microtransaction economies become economically viable. The cost barrier for digital ownership, it virtually vanishes.
And then there's TreeChat, which is focused on privacy.
Yes, demonstrating how to restore privacy to communication. They're leveraging the peer-to-peer structure of the underlying network to build social media where users, not centralized platforms, control their own data.
That's a pretty fundamental shift.
It's an application that absolutely requires the integrity and the scalability of this base layer to function securely at speed.
And is this accessible for developers, or do you need to be a blockchain specialist?
That's a key point. The sources highlight the Adds-Overlay JavaScript package.
JavaScript, okay, that's huge.
It is. It transforms all these complex blockchain interactions like handling Merkle proofs or creating specialized transactions into familiar web development patterns. It drastically lowers the barrier to entry for millions of developers.
This has been a really deep dive into some genuinely revolutionary architecture. We've laid out the difference between unbounded horizontal scaling and traditional limits.
The continuous confidence you get from subtree validation.
The formal security model of SPV that allows anyone to participate.
And the practical accessibility from tools like ARC and that JavaScript package.
The takeaway here seems to be that this isn't theoretical infrastructure. It's proven, it's production ready, and it's handling massive data volumes right now.
Terranode has really achieved what so many in the space said was impossible. It has definitively answered that decade-old question. Can blockchain scale to serve global applications at enterprise volumes?
The sustained testing results seem to have settled that debate.
I think they have.
And if the question of scale is truly answered, then the new frontier is purely one of application and, well, imagination.
And that leaves the ultimate provocative question for you, the learner, to carry forward. Now that we know the infrastructure scales unboundedly, the challenge becomes,
what will we build now that blockchain scales unboundedly?
think about the limitations in your own field, the regulatory bottlenecks, the data integrity risks, the transaction costs, and just consider how this new foundation might make those old limitations obsolete.